Welcome, everybody. Thanks for coming. So what we're going to talk about today is how to get more geophysicists hooked in and interested for the future, engaging students with instrumentation and at the undergraduate level. You'll hear us talking about teaching resources that all fit under an umbrella called Geophysics Tools for Societal Issues. This project this overall program brings together projects that were originally started by UNAVCO and community partners in Idaho and Indiana. The Iguana project started by Iris with some of the partners here, Andy and Sarah, and also from Rutgers. Also work in collaboration with the Science Education Resource Center and the National Association of Geoscience Teachers. The Geophysics Tools for Societal Issues, GETSI, is currently supported by EarthScope through the Gauge and SAGE facilities. Even though this is more of a webinar setup, we really do want to hear from you. So please use the Q&A box to enter questions as they occur to you. We may answer some by typing right away, or we will get to them by the end, but feel free to put them in the chat or in the Q&A, as they occur to you. In today's webinar, overall, we're going to go over why use geophysics, instrumentation, and data as a way to hook in students and keep them engaged, potentially start them in being engaged in geoscience and geophysics. We're going to overview the teaching modules and methods that in the near surface that we have in these teaching modules, how to borrow instruments from EarthScope if you don't have access to them, workshops that instructors could take this summer, a bit of time to explore the resources, and then some time for discussion, thoughts, and questions. But first, we wanted to start with finding out a little bit about who all is in the room, so to speak, right now. So we're curious. There's 3 questions that we just put into a poll. Subdisciplines that people are teaching in, what level you might want to teach these sort of instruments at, and what sort of experience level you have specifically with near surface instruments. So we'll give it a couple minutes for people to put in answers there. All right. About 2/3 of the people have answered almost, so we'll give it another fraction of a minute and then we can see the results. Okay, I'm going to say that we are done. So I'm going to share the results. Hopefully people are seeing the poll results in front of them. So what we can see is that there is a very high level of people interested in teaching specifically geophysics with these instruments, so geophysics classes, with a little bit of other classes such as geohazards. People are definitely looking towards the majors level, about half overall, but a solid number also at introductory majors courses. And finally, there's quite a spread of people from no experience to very experienced, with the majority of people be sort of in the middle. So keeping that in mind, we will aim our talk today for that audience. And now I'm passing it to Andy.
Thanks, Beth. So I'll start out by talking a little bit about the program goals, sort of why we set out on this direction and what our objectives were to get there. So really what we want to do is attract the widest range of possible students to geophysics. So we know that there's a lot of students out there that are interested in geoscience, environmental science, a variety of Earth topics, but we want to get the word out about geophysics and make it exciting and engaging. Our next goal was to develop curricular materials, so teaching materials that highlight how varied the applications of geophysical tools are, including what we could sort of focus on environmental problems in urban settings. And I'll get to why that's important in a slide or two. And our third goal was to focus on societally relevant applications. So things that the students hopefully will connect with that might be going on, in the world around them. Next slide, Beth, please. So the whole motivation here to use societally relevant themes is based on the idea that, well, students are going to be more excited about learning about geophysics if they can understand why it's, related to something that they either know about or potentially experiencing themselves. We tried to design the curriculum materials around an engaging structure of lecture slides, but also the structure of how the materials are presented in terms of everything from PowerPoints to recordings to labs and practical exercises. And we include varied and early and frequent assessment that enables the instructor who's using these curriculum materials to dynamically revise or edit or reorder some of the materials that we're providing or augmenting their own curriculum materials. Our content shows is aiming to show how practitioners from a wide variety of backgrounds have a place in this discipline. So whether you're coming from somebody who might be interested in civil engineering or interested in environmental science or interested in geology, there's a lot of opportunities to be excited and interested about geophysics as well. So we want to just say that this is not just for the folks that come in from the math and physics side, but there's a wide variety of backgrounds and disciplines that can find something exciting and engaging with shallow geophysics. Thanks. Next slide, Beth. Yeah. So the whole motivating underlying point here is that in order to engage this broader range of people from different disciplines, if we want to do this, how can we expect that they're going to do it if we don't consider their perspectives, their needs, and importantly, their motivations? So what motivates students to be in geoscience in the first place, and how can we sort of speak to that with these curricular materials focused on geophysics? And we sort of base it on the theme of these principles listed on the bottom left here. We want to leverage the students' interests. We got to know what their interests are, but then design the materials to leverage that. We want to know what their goals are and design the materials to actually work towards that. And then potentially also leverage their experience. So what things are they likely to be familiar with in their day-to-day life experience that we can engage with to make this the most exciting material possible. We want to cultivate some identity and a sense of belonging within STEM, and we want to be responsive to situations and the context of, for example, environmental problems. So one example of how we've done this in the GETC materials is by focusing on these urban areas that have many potential students just because of population density in urban areas, and potentially a lot of easily accessed field areas that have relevant issues. And these might not be the quote unquote wildland field areas that many of us are used to, but field areas that have issues along the lines of, well, how do we build buildings or infrastructure, or what do we do about contamination, or finding things that are buried below the surface? Next slide, Beth. So one thing that we were thinking about when designing these materials are, what is preventing students from actually being engaged in the field of geophysics, and how can we, aim our curriculum materials to promote effective learning? So a few of the barriers that I think are good to sort of put out here, so everyone's kind of familiar with, what we were thinking is, first of all, there's potential for lack of knowledge or misconception about the geosciences, right? So in many cases, students may not have a geology course until high school, or maybe they don't even get to have a geology or an earth science or an environmental science course in high school. So there's just limited exposure. And then getting to undergrad or getting to a 2-year college, it may not even seem like an option just because they've never heard of it or been exposed to it before. And in some cases, it's actually curricular requirements in the K-12 education that prevents the teachers from bringing in geoscience requirements. And this is obviously very different across the country, so it's hard to kind of predict what that might look like. So we want to try to overcome this issue of lack of knowledge or maybe misconceptions about what geoscience is and why students may want to consider that in their education. There's potential cultural barriers that have to be overcome. The easiest sort of example of this is that there are families that perceive that professional training, like medical doctorates or law degrees or engineering, are preferred college majors simply because they can be, they're perceived to be easier to connect to a future high-paying job. And as we all know, there are plenty of future high-paying jobs in geoscience as well. So, trying to provide the information for students to see that there may be really good opportunities in the career fields out there that are beyond what they may have just heard about at home. And then the third barrier is that there may be some aspects to geoscience or geophysics that are really attractive to privileged students, but maybe undesirable to students from historically marginalized groups. So the easy example for that is that a lot of geoscience students come because they want to be outside and like to go camping, but that might not be something that's familiar to folks from urban environments, right? So trying to balance that out a little bit more and show that, well, you don't necessarily have to get dirty and not shower for a week and be in the wildland environment to do cool geophysics that have really high impact on society. Next slide. So the next question that I'll talk about quickly here is why we focus on curriculum. So the education system is a system, and we want to transform that system to be able to serve the students best and highlight these scientific themes that are exciting and compelling, right? Curricular materials are a critical component of that system. We want these curricular materials to sort of follow this attract, support, prepare framework. And this sort of follows on the idea, as I said in the previous slide. We want to have material that attracts students because it speaks to things that are related to what they're passionate about or what their goals are, right? We want to have curriculum materials that support the students. So support in the sense of helping them to, be able to access the content, even if there's math that they may not be familiar with or concepts that they may not have been presented in previous years of schooling. And then finally, we want to prepare the students for the next stage, whether that next stage is just, do I want to be a geoscience major or a geophysics major? Or maybe that next stage is what that career is. So providing them with the information they need in order to make that decision and actually be successful in the next stage of their education. Next slide.
All right, thanks, Andy. I'm going to now just quickly run through the different methods that are featured in the teaching resources and which ones the instruments can be borrowed through the EarthScope Primary Instrument Center. And then we'll go into each of the methods and modules in a little more depth. So the near surface geophysics methods, sort of traditional near surface, that we have ground penetrating radar. So radar radio waves, pulses that reflect off of targets underground. Electrical resistivity, so that's direct current applied to the subsurface to see where it flows better or easier. Seismic refraction, so that's sound waves that bend at geologic interfaces, and magnetics and gravity, which are these passive fields that we can measure contrasts and physical properties with. So all of these modules have prepared data sets and case studies, but 3 of the 4 methods can be used with instrumentation from EarthScope. The geodetic modules, there's global positioning, so satellite signals to determine location. Structure from motion photogrammetry can be used to produce high resolution topographic data. We also have information about terrestrial laser scanning, and we do have those instruments, but we found that they're not generally the best at the undergraduate level. So we do recommend these other 2, structure from motion and GPS. So I want to show you a little bit about what's in the modules, and then we'll start to walk through quickly each of the different modules and methods. All of the modules were developed through a rigorous process of development and testing. They were written by other faculty members who were writing for things they would want to teach with. And we had varied author teams with different backgrounds, and they were tested in other classrooms just to make sure that they can be used effectively in a variety of classes. You can see that this one is primarily aimed at the 300 to 400 class level, but it has been successfully used in intro classes and community colleges as well. The early parts of the modules have the method introductions and also the motivation, like why do we want to learn this? What are the fun and interesting problems we could address? And then feature a variety of applications. And in this case, like, well, there's different types of field areas. And so maybe one of these, a road cut, a fault scarp, will be available near to someone. Not all of them, but any one of them could serve. And all of the modules have learning goals, and at the more unit level, at the individual unit level, more specific learning outcomes. So for instance, this one is that students learn to design and conduct a survey that addresses a geologic question, that they're able to articulate the impetus for why society would want to investigate that given question, and where appropriate, justify how the technique was chosen, or weighed between, say, structure for motion and laser scanning. A little bit about the structure from motion method. It uses changing camera locations to build a 3D point cloud model where you know where the XYZ coordinates are of a bunch of different points. It's pretty much the same thing that our eyes are doing, which is taking two slightly different locations and the slight difference in those images and being like, I can see a 3D world. It can be done with drones. It can be done with handheld. That works really well at the undergraduate level, and also things like tall poles or kites or balloons. They can be turned into a variety of topographic data sets, from shaded relief to photorealistic digital elevation models, and many other things that can be used in GIS. The applications can vary from hazard analysis. This is an example of using changing topography to follow a creeping landslide, or this is a post-flood. They could see that the thalweg of the river had been reamed out more. Engineering geology can use the geometry determined from rock outcrops to design better road cuts, or it can be used for paleoseismic trench careful documentation before they need to be filled back in, or even things like archaeology. The GPS module, again, starts with an introduction and motivation. And then for the instrumentation use, the kinematic or RTK, real-time kinematic GPS, GNSS units are the most appropriate for things like measuring topography or change detection. How GNSS GPS works, it determined locations by 4 or usually more than 6 satellites. This enables solving for the 4 variables of X, Y, Z, and time, because clock quality on the receivers isn't as good as the ones on the satellites, uses trilateration and can determine precise locations. The RTK, or real-time kinematic method, works with having a base station over a known point and a rover with radio connection to that base station. And so both of the receivers are listening to the satellites and getting data, but the rover, which is moving around, is also getting corrections from the base station. And that allows one to come down to a centimeter or so scale accuracy. This can be used for things like creating a topographic data, running around all over on an area that you don't have LiDAR, say, for, and you can generate GIS topographic model. Can be change detection. This is a class that has put pins in a creeping landslide, and they revisit it every semester and can see where the movement is occurring, or in many cases, georeferencing other surveys. So that would be, in this case, a structure from motion drone survey, or 1,000 nodes in a seismic array, or a GPS or GPR unit here with the GPS on it and a base station over here. So a lot of times the GPS is just used to know where other stuff is. All right, back to Andy.
Thanks, Beth. So I'll start by giving an overview of what the content is in the seismic refraction unit. So the seismic refraction module contains 3 units, in addition to some instructor materials that give a general overview. The first unit is a very basic motivation, sort of understanding why students might want to apply shallow seismology to explore the subsurface environment. It also includes some comments on careers and, yeah, sort of mostly context. Unit 2 is where we get into actually how things work. This mostly focuses on Snell's law. And it provides the basic physical background that the students need to be able to understand why seismic refractions work, why the rays are turned back towards the surface, and we can actually observe the waves as they interact with the geophones, and actually are able to retrieve some information about the subsurface structure. And it also goes over the background of actually calculating a simple, two-layer model with the velocity of the top and lower layer and the thickness of the upper layer from a raw data set, right? So it goes through the principles and the technical elements that are needed to do that. And then the third unit is where we bring in the real data. This is a data set that was donated to us on a real seismic study at Corduroy Creek in York, Pennsylvania, and they were doing some urban renewal, and they had to do seismic measurements to actually plan how they were going to sort of do urban renewal along this creek corridor. And so in that, students actually take raw seismic data, extract first arrivals from those data sets, from the waveform data sets, and then they calculate that two-layer model for depth to bedrock in this case. And then they interpret that in the context of the case study, right? So how would you actually use this information to guide how their urban renewal project is happening? There is additionally a collect your own data way to do it. So you can either use the provided data that we give you, or we give you instructions if you are to take advantage of the instrumentation that Beth mentioned earlier. If you want to do that, then you can bring the instrumentation to your own campus and then kind of set up a similar kind of concept and do that instead of the case study or in addition to the case study. Next slide, please, Beth. So I think most people on this call are very familiar with geophysics, but I did notice that it seemed like about 50% of the participants were either in the less familiar category or not experienced, at least with shallow geophysics. So I'll really talk briefly about the seismic refraction method in case it's not something you have encountered before. So the idea with seismic refraction is that we have a source, which is the star in the top left here, that's going to send acoustic waves into the subsurface. And at interfaces of velocity contrast in the subsurface, we turn those rays where they travel along the refractor and are sent back towards the surface where we can observe them with the geophones. So this is not like reflection at all, where we get images of the structure that way. We are interpreting the refraction arrivals in terms of how they interact with the subsurface to extract the information about the velocities. So on the right side, you can see the travel time offset plot that we get from picking waveform data from a data collection, and you have downgoing leg, which is the green circles that indicates the direct arrival, and then those refracted arrivals are the red dots to the right of the downgoing leg. And so by picking the slopes of those two different legs and then looking at how the time intercept, that's the T1 on the y-axis there, then we can calculate that one-dimensional subsurface structure model with velocity of the top layer, velocity of the lower layer, and a thickness of the top layer. Next slide, please, Beth. So some examples of applications that we envision may be engaging to these students. So infrastructure planning is something that's the one that we highlight in the unit here. Something like depth to bedrock will give you information about how deep you would need to dig or how difficult it might be to dig in order to put the foundation for a building or bridge or whatever in a whatever environment you might be working with. Seismic refraction is often used for water resources studies because you can estimate porosity from those velocities. Seismic refraction can be used for environmental remediation. Usually it's related to imaging the structure so that you can figure out where contaminants may have moved. And then also things like geohazards, potentially, imaging landslide, susceptible areas, and things like sinkholes and things like that. Yeah, next slide, please.
So I'm going to talk about the GPR module, which has 3 units. The first one is an introductory unit that discusses GPR in the context of medical imaging techniques that students might already be familiar with, and a little bit about wave propagation. And then the second module gives students a chance to work a little bit with real GPR data. We've developed an app that lets them fit the pattern of returns from point-like objects, and from that to determine the velocity of the radar wave and how deep the object was that produced that diffraction pattern. And then in the third module, we discussed some real case studies and some of the limitations of GPR. One of which is when you get a return, it can be hard to tell what it is. Is it a tree root? Is it a grave? And some discussion about that. And we also have added a considerable amount of material about how you might collect your own data on your own campus. So the seismic method doesn't give you an immediate result, but students love that it can record their footsteps and stuff like that. GPR is satisfying with students because the data come out in real time on the screen. You can see it as it's coming. Next slide. So the GPR method is really very similar to reflection seismics, except instead of having a single source and an array of geophones, you have a single transmitting antenna and a single receiving antenna, and they're mounted together. In this photograph, they're both in the yellow box, and then that is pushed along the ground. And the figure on the right shows an example of a screen snapshot from a video that's part of the module that demonstrates how radar waves go down into the ground and respond to like a buried point object, like a buried pipe, and what the record looks like from that. And if you're familiar with seismics, you'll see that unlike seismics, the air wave is faster than the waves in the ground. Next slide. So what are the kinds of things you can do with GPR? It's widely used in Florida for sinkhole investigations, both for the sinkhole itself and for the overlying sedimentary stratigraphy indicating subsidence. It works really well in young volcanic terrains. It's also used in dry sands to image dunes, and it works in ice and snow structure. And all of these applications, though, are really location specific. So if you don't have those on your campus or where you could do work, the rest of them are widely available. GPR is good at imaging the location and depths of tree roots, buried utilities, graves, and other archaeological sites, and it can be used to look for rebar within concrete. And this last application will work anywhere in concrete. So if you got your equipment on loan and you discovered that you have clay-rich soils that are good conductors, so the radar wave doesn't penetrate very well, you can still do good studies of the concrete in your buildings. Next slide, please. So the resistivity module has 5 units, and it really goes much further into the method than the GPR unit, which really stays at an introductory level. And not only does it discuss what geophysicists would call the resistivity method, but it discusses some electromagnetic methods that also are sensitive to the resistivity structure of the subsurface. And this is all done in the context of a visually beautiful materials describing a real urban wetland. And we've added material on how guidance on collecting your own resistivity data, and recently a new intro to resistivity animation that's now live on YouTube. Next slide. So how does resistivity work? You put an array of metal stakes in the ground called electrodes and connect them up to a control unit that in turn drives current between a pair of electrodes. And that current flowing in the ground, it's a DC current, generates voltage differences or electric potential differences at other locations on the ground. And these potential differences are measured at other pairs of electrodes. And by driving current from multiple pairs, like as shown in the lower left diagram, and measuring voltage at different locations, you can effectively sample the resistivity of the ground over different areas, volumes beneath your electrode array. And then those raw readings are put into a code that inverts the data for the resistivity structure of the ground beneath your electrode array that could produce the readings that were taken. Next slide. Maybe I'll just add, in the context of the last one, it's labor intensive to set up the array, then it takes maybe an hour or two for the equipment to acquire the data, and then you take the array down. After that, it's relatively quick to do the inversion. There's some beautiful open source software to do it with. Okay, Beth, thanks. Next slide again. Okay, so what are the kinds of things that resistivity works well for? Wetlands, the freshwater saltwater interface, leachate plumes, where the leachate can have a higher conductivity than the background groundwater. Caves, an air-filled cave will be more resistive than rock. Zones of weathering, in particular, igneous or metamorphic rock that are weathering to clays and saprolites, will have a distinctive resistivity signature. You can image the water table and differences in groundwater associated with agriculture or infiltration patterns, as well as stratigraphy, in particular clay layers, will appear as low resistivity layers. So there's a lot of different kinds of applications you could explore. Next slide. So the gravity and magnetic units are bundled into a single module for potential fields. The first two units are introductions to gravity and magnetics. And the third unit lets students work and process real field data. So that would work well for a real geophysics class. The introductory modules are largely based on students watching videos and working through questions related to those. Next slide, please. So gravity, you're probably familiar with it. You just have an instrument, a gravity meter shown on the right. You take point measurements of the Earth's gravity field at different locations. These modules explore near surface applications, so not the tectonic scale uses of gravity that you're probably more familiar with, but we discuss concepts of like if you had a tunnel or an ore body. Next slide. So yeah, students work through applications thinking about what kind of gravity signature you might get from sinkholes or changes in groundwater. But a beautiful application that Andy developed and gives data for is that you can measure the decrease in gravity as a function of elevation on a couple of flights of stairs on a campus. And this works really well. Next slide, please. So magnetics, like gravity, you take an instrument out and make point readings of the Earth's magnetic field at different locations. And you could take data like 1,000 times faster with magnetics than with gravity. So people often make maps of the gravity field. And in the next slide, talk about applications. In the near surface, most applications are essentially using a magnetometer as a metal detector, but there's a lot of practical applications: abandoned wells, storage tanks, UXOs, metal archaeological material, buried infrastructure, and on a smaller geologic scale, it can be useful for detecting contacts between igneous rocks and like background sedimentary rocks. The figure in the lower right is a magnetic profile we collected last week in my class, where we walked with our cell phone magnetometers over a buried culvert that, so if you have large buried metal, you don't need a magnetometer at all. You can just have students use their cell phones. And I would add that there's a considerable amount of employment, like in my state of Florida, directly for students coming out with skills with ground penetrating radar or a magnetometer for applications like the ones we've discussed here. So you can motivate students with the prospect of a working job in the earth sciences with just a bachelor's degree with skills like these. Okay, I think that's it for me.
Thanks, Sarah. Yeah, and maybe I'll add, I did specify that EarthScope does not yet have magnetometers or gravimeters to loan out, although they are rentable from places like the University of Wyoming. But everybody has an iPhone or a phone of some sort with a magnetometer in it, and there are exercises in the module where the students can collect their data that way. So that's delightfully tangible, I think, for students to be able to use their phones. So now I wanted to talk a little bit about how if you don't have the instruments on your own campus, how you would access instruments through EarthScope. And so we have a geophysics field education page that I'll jump to in a minute. That's sort of a one-stop shopping for going to all the different places you might be interested in related to teaching with geophysics instruments. It has the list of equipment available from EPIC, which is the EarthScope Primary Instrument Center, and instructions for submitting your request. The cost is only shipping. And as I mentioned before, we have seismic geophones, GPR, electrical resistivity, particularly one called a Super Sting. We have kits of GPS. So usually in RTK GPS, you would have a base station and one rover, which isn't very useful for a 20-person class. But we have kits where we can send out 4 or even more rovers if you have a large class, so that you can have students in smaller groups working on things. It's the cost of shipping fees typically, but waivers are available for low resource institutions. So hopefully, yeah. So going to this web page, this is what the web page looks like: Geophysics Field Education. The first tab is Instrumentation, and down here under the purple text is sort of a walkthrough of how you would use the request portal. The request portal was kind of designed for people with funded NSF projects, and so this gives you step-by-step guidance on how to fill it out for an educational request. We have some pricing estimates on the shipping costs. On this page, we also have teaching resources that link out to the Geophysics Tools for Societal Issues program page. And this has all of the manuals embedded in the different modules, but I also put the manuals in this one spot. So if you want to not remember that the ground penetrating radar guide is in Unit 3, you can come here and find both the instrumentation and the software guides for each of these different methods. Okay. The other thing I wanted to, so that was accessing equipment. The other thing I wanted to mention is that we actually have 2 workshops going this summer to help instructors at the undergraduate level, and that can include graduate students and postdocs who have teaching interests or teaching responsibilities. One is an in-person course teaching near-surface geophysics to undergraduates from intro to majors. That will be a 3-day course held at the Colorado School of Mines campus and co-hosted with the geophysics department there. It will focus on GPR, seismic refraction, electrical resistivity, and GPS. You can read more about it at the workshop page that I believe Scott just dropped in the chat. And that will include hotel accommodations and food during the workshop and a reimbursement for up to $750 of travel. Teaching in the field with structure from motion and RTK GPS is going to be a virtual course. It will be 2 weeks later, so that's August 11 through 15. It will have synchronous, like class time, and asynchronous components. And in the end, people will learn to make a georeference point cloud. All the people accepted to this workshop will be sent a pair of instruments so that they can practice them, like have a classroom session, go out and measure something, and work through the process that way. Multiple participants from the same institution are encouraged. So if you are interested in doing that, see if you can recruit a couple other people so that each instrument pair that goes out gets learned on by more people. The application deadline for those workshops is tomorrow. So if you're interested, I encourage you to look at that and apply sometime before the end of tomorrow. These are for US citizens, residents, or people at US institutions. We can't ship equipment internationally for this, and the travel support is for people that are associated with US institutions. So sorry, because I know we have a big community that is international, but I look forward to you using the teaching resources, which are free and online for anyone with an internet connection. It's just the instruments that we can't ship out. So what I would invite people to do at this point would be to go to a module that interests you. Think about like, what method might I like to teach with? And I think Scott is going to drop into the chat another time on the Getsy front page. But so pick a method, one of the modules. What are you interested in teaching? What instruments are you interested in borrowing? What questions might you address in your course? Are you interested in some of the urban questions? Or might you have a more remote field area that you have interest of? And what questions do you have to us? So feel free to put in any comments that you have here, like things you find that were aha moments or interest to you, or any other questions that you have for us about how things work. We'll give people, maybe until about the 5 to 7 minutes or so, just to get some familiarity with the resources, and then we'll go back to verbally answering some of the Q&A questions that you put in. So I see that Scott did put the link into the Getsy page there.
So I think we'll wait another minute or so here, but please do put your questions into the Q&A. Once we have a couple, we'll start talking about those. All right, Beth, well, while people are looking, do you mind if I throw in a question at you? I'll buy you some time. I was curious if you could talk a little bit about how easy it is to use some of these modules in a modular way, so that if folks have differing amounts of time they're able to dedicate to that topic in their course, like, can you pick up a piece versus a whole block? Like, how are things set up like that?
Maybe I'll start by speaking to the modules I've been involved in, and then Sarah and Andy can add. But we intentionally designed all the modules to be very submodular, if you will. So, and the research that we've done on how people use the modules show that the typical way a faculty member uses the module is how they want to, for how it works in their course, and whatever piece of the module they like best. So in very few cases is it an entire module, and much more commonly it's whatever nugget they want, plus it's changed for their particular teaching situation. And that results from that have shown that people are satisfied with the modules and want to use them again, whether they used a little bit or a lot, and how much they changed it. So yes, very designed for flexibility.
Yeah, they're modulars that are module, but they're modules that are modular, right? So we have, you might want to use a PowerPoint to talk to the class, but then use your own lab experiment. You may want to have your own PowerPoint, but just use our data, right? So it's all very flexible like that. And we kind of envision that, you could kind of stack up all of the modules and make a whole class out of it if you needed to come up with a geophysics class at the last minute for some reason. In contrast, you may just pick a few things here and there, maybe even just grab a slide or some graphics from the slide, right? We're giving you all the PowerPoints, so you can go in and just pick and choose whatever you want, delete slides, hide slides. So yeah, it's all meant to be something that you can either use kind of wholesale or really adapt to your situation if you're more experienced.
And if you're less experienced, I think they really is an opportunity to be like, maybe I'll just do unit 1 this time. And then next year I'll do the unit with the instruments, and that it can work either way.
Okay, we have a couple questions in. We can start there.
Mm-hmm.
So the first question is asking about kind of the depth that the gravity and magnetics units in particular are able to look down, or what kind of data are they working with as they're set up?
Yeah, you can see quite deep with these methods, but you have to have very large surveys to do so. So I would sort of think if there's some depth that you wanted to see to, think 2 or 3 times that in horizontal scale at least, to make, to get, because the deeper the object, the broader the signal.
And so maybe I'll just jump in and say one of the things I've learned over the almost decade of sort of helping integrate instrumentation into undergraduate is small field areas are better for your first foray into it. Now that might not be true for an advanced geophysics course, that has a large field component and also some research aspects, but a lot of times, starting small is actually a better way to make sure you have a handle on it with your students. So, and then decide where to go from there.
All right, next question we have here. I wonder, is there any survey to the students on how effective the knowledge taught in these modules is for helping their career development?
Andy or Sarah, do you have anything from Iguana that you want to say? Iguana was the name of the modules that they started with before we brought it under the larger umbrella. Maybe I'll start talking and see if, oh, go on, Sarah.
Yeah, our surveys were always immediately like post-use, so we can't speak. We don't have that data, like looking back over a few years, like how useful was this? So unfortunately, no.
Longitudinal student data is non-trivial and kind of expensive to get. So I'll have to say, what I can say is that all of the modules were pilot tested in several classes, and the feedback on the students and what they did and did not get out of it was factored into the final version, and the revisions and things like that were made. And we're continuing to revise things to some extent as we get more feedback. There's a separate project that has been done with a very limited number of students, which was more specific. They're called it's called Explore. It's not this project, it's another project that was working with students and their understanding of geophysics, introductory level students at Fort Valley State University. And it did show that interacting with these, with geophysics instrumentation and thinking about geophysics careers did impact and increase the amount that they went into it. So I think it's all part of the same pie, if you will, although I cannot say we have rigorously tested it scientifically at all pie pieces.
All right, next question here. Are there any modules in here for deep interior geophysics, for not near surface, or any plans to do that in the future?
Not immediately, but I'd be happy if you want to email me and give some ideas. We have a variety of modules, more geodetic, that do a lot of different parts of the earth, if you will, and that could be considered. There's higher level resources that EarthScope is working on related to magnetotellurics, but that would not be aimed at the undergraduate level so much as the graduate and research level at the moment.
So we view near surface geophysics as the on-ramp to deeper, more potentially complicated or yeah, harder to
Esoteric.
visualize geophysics, right? So, like Sarah said, students love getting out there and whacking the ground with a hammer and seeing their footsteps, show up on the the geophones. And that's kind of like what we're trying to leverage here is like hooking them in and then, once they get geophysics is cool, then go on to the more complicated stuff in deep interior geophysics.
But I will add that, it's a great starting point because radar waves work like seismic waves, and seismic refraction works in the deep Earth's interior, same for magnetic and gravity. So starting shallow is a good basis for the same science you use when going deeper.
And EarthScope does offer a summer program called the Seismic Scale Building Workshop. So I don't know if you have that link handy, Scott, but we that will start in June. I think the the registration will open fairly soon for that. And that is aimed at the undergraduate to graduate, early graduate level, and that gives a lot of skills in seismology. And so if students get interested enough in your regular classes that they're like, seismology, yes, that is a summer course where they could build a lot of the coding skills and things like that that they would need for deeper Earth.
Okay, we also have a question here, follow up on what Sarah said earlier. The use of a phone as a magnetometer, is there like a specific app you would suggest for that, or how would they do that?
Yeah, I actually just explored this semester. I would strongly recommend an app called Phyphox, spelled Phyphox. They don't share your data. They don't try to sell your data to anyone, and they record the data and you can dump it out in a really easy way. It's really a lovely app. Yes, thanks, Beth. Something like that or close to that.
That's cool. I haven't heard of that one, so thanks. I'll go look it up. I've used one called Science Journal, but I don't know anything about what they do with my data. That's the one I used during the COVID to help develop some exercises.
I was thinking about the longitudinal study, Beth. And so this is not a direct answer to the question, but USF did a survey of our alumni, and so people even 30 years out, what they thought was most important that they had learned, and they really valued their field experience. So in the context of this webinar, I would say, if you want to make a lasting difference in people's lives, link the course content to an actual field experience if you have the resources and the time to do so. That makes a big difference.
And the field, again, can be very close or on campus, even potentially. Well, we're very near the end. And so I think what I'll just say at this point is if you would like to hear more immediately when there's new teaching resources or there's going to be another module or, another workshop coming out, send a blank, and this will go into the chat there too. Send a blank email to teaching-geophysics plus subscribe at earthscope.org. And whenever we have something happening, it doesn't spam you all the time, but when there is a real event or a real resource that we think you might want to know about, you'll get a notice.